Hello friends, my name is Shreyan Shah. I am here to discuss one of the emerging technologies of semiconductor, which is organic field effect transistors. The outline of this topic are how to design organic field effect transistor, how to prepare organic field effect transistor, transfer characteristics of organic field effect transistor, carrier transport, advantages and application of organic field effect transistor. Organic field effect transistor is a field effect transistor using an organic semiconductor in its channel. They can be prepared by vacuum evaporation of small molecules or by solution casting of polymers or small molecules or by mechanical transfer of peeled single crystalline organic layer onto a substrate. They are fabricated with various device geometries. Out of them, the most commonly used is bottom gate with top drain and source electrodes, as it is similar to thin film silicon transistor, using silicon oxide as gate dielectric. Organic polymers such as polymethyl methacrylate can also be used as a dielectric. Organic field effect transistors adopts a architecture of thin film silicon transistor. With the development of conducting polymer, the conducting properties of small conjugated molecules have been recognized. The performance of organic field effect transistor has improved significantly in terms of on or off current ratio and can compete with the performance of thin film silicon transistors. One of the main attraction of this technology is that all the layers of an organic field effect transistor can be deposited and patterned at the room temperature by combining low cost solution processing and direct write printing. Now we will discuss how to prepare organic field effect transistor. Thermally oxidized silicon is a traditional substrate for organic field effect transistors, where silicon dioxide serves as a gate insulator. The active field effect transistor layer is usually deposited on the substrate by thermal evaporation or coating from organic solution or electrostatic lamination. Thermal evaporation and coating techniques result in polycrystalline active layers as they are easier to produce, but they result in relatively poor transistor performance. The schematic of organic field effect transistor is shown in the figure. Electrostatic lamination technique is based on manual peeling of thin layer of a single organic crystal, so it results in a superior single crystalline active layer, but it is more tedious. The thickness of gate oxide and the active layer is below 1 micrometer. Now let's see the transfer characteristic of organic field effect transistor. The transfer characteristic of organic field effect transistor is shown in the figure. The charge in the channel is modulated by adjusting the gate voltage, so the device behaves as a variable resistance. When the gate voltage is applied between source and gate, majority carriers accumulate at the insulator semiconductor interface, which leads to the formation of a conduction channel between source and drain. Now let's see how carrier transport take place in organic field effect transistors. Carrier transport in organic field effect transistor is specific for two-dimensional carrier propagation through device. Various experimental techniques such as transverse time of injected carriers, time of flight to determine carrier mobility, organic monolayer experiment for probing orientation dipolar changes, optical time resolved second harmonic generation, etc. for the studies. Carriers propagate through polycrystalline organic field effect transistors in a diffusion-like manner. They move through the conduction band in the base single crystalline organic field effect transistors. The most important parameter of organic field effect transistor carrier transport is carrier mobility. The evolution of carrier mobility over years of organic field effect transistor research is shown in the graph for polycrystalline and single crystalline organic field effect transistors. The graph reveals that the mobility in polycrystalline organic field effect transistors is comparable to that of amorphous silicon, whereas mobility in organic semiconductor such as rubrene based organic field effect transistor approaches that of base polysilicon devices. Now let's see the advantages of organic field effect transistors. It is less complex and lower cost fabrication. We can use solution processing and photolithography patterning for organic field effect transistors. It can be manufactured at lower temperatures of 60 to 120 degrees Celsius. It provides mechanical flexibility as it is compatible with plastic substances which are foldable and lightweight. It has strong optical absorption and efficient emission. Organic field effect transistors can be used in flexible, low weight, large area displays such as organic LEDs and organic thin film silicon transistors. It can be used also in optical recording, which is based on optical absorption. In electronic circuits printed on papers and electronic papers, organic field effect transistors are useful. It is also used in ultra low cost, low performance applications such as smart cards, and it can be used in low heat dissipation circuits. Thus, we can say that the organic field effect transistor is compatible with huge varieties of substrate, such as web coated polyester and papers. It is reliable readout according to product requirements. It can yield enabling profitable manufacturing. It is a proof of concept for simple and cheap manufacturing methods. We can bring down the supply voltages to 1 volt. Thus, the organic field effect transistor is ready to meet the requirements for product realization. Thank you.